This is the fifth episode of the series where we together implement runtime immutability checks library for Go. And today will be once again short episode when I try to recap and give you some additional details on the recent changes. This one is also a little bit different than previous one because we're going to review changes that were made in 4 different sessions. That's why we are currently viewing everything through GitHub. So on GitHub, you can see pull request for every separate session. And and we will try to go through every PR and check the most significant things that worthwhile mentioning. So let's take a look at the first set of changes that I've made after the previous episode. So, as I mentioned before, I started to work on first benchmark suite and started to do some small first kind of improvements. And yeah, that's you can see the results of all these things here. So in terms of benchmarks, let's see what we got. I'll try to show you what is our approach to benchmarks right now. So if we just view file, so as you can see, we kind of iterate between different types of loads. So first of all, we have different set of settings that we want to check. Basically where we capture everything, capture snapshots and file origins and basically stack traces. Yeah, and we allow inherently unsafe types, or we don't allow them. Yeah. Then we have a set where we don't capture origin of a snapshot. The other thing where we capture string snapshot, where we skip capturing string snapshot of our immutable value, and the last setting is where we don't capture anything basically. Yeah, so and then we have two sets of benchmark. One benchmark is that where we have just a 16 kilobytes byte slice, and we basically check how quickly we can capture a snapshot of this byte slice and then verify that it was mutated. We have also different settings where it's never mutated, and when in 1% of all cases it gets mutated. Yeah. What else? The other set of benchmarks creates a very complex kind of nested object. It creates like a slice of 8 of those objects, and then every of those objects has like a slice of strings which is pretty big, like 1000 strings. But every string can be kind of 4 kilobytes on average or 2 kilobytes on average. I don't remember exactly. We will take a look later on. Yeah, so this is um, our benchmark for bytes. As you can see, it just allocates a bunch of pre-allocates a bunch of byte slices, and then it basically fills all these byte slices with random bytes. And after it, we kind of reset all timers because we don't want to kind of measure the actual test data creation. And then we start to do all these things, like we capture snapshots. Yeah, in one, if we want to mutate things, we kind of um, random value. Yeah. Yeah, so if we want to mutate something, so if mutation percent is higher than 0, we will basically mutate first byte of the whole byte slice, and then we will check the others, we will create the other snapshot, and then we basically will compare snapshots between each other. So that's it. That's the first test case, like benchmark suit. And the other benchmark suit is a little bit more complicated because we use this function that creates these transactions for us, and transactions can be pretty big. So transactions, I tried to replicate kind of some domain objects and nested structures and so on. So we have like a currency enum, we have amounts, which is just a kind of an alias. We have currency codes, yeah, a bunch of things. You can take a look if you want. We have like money type, then addresses. What else? And then kind of transaction. It's source account, destination account, how much money we going to transfer. We capture like previous snapshot. So snapshot is like previous state of source and destination account, and then we capture after transfer the states of source and destination accounts. And then we have like transaction context. It's like a slice of strings, which can be very, very big. In our case, it's like 1024 elements. And then we have a map of attachments, which is also like map from strings to interfaces, to empty interfaces, and we have a bunch of other things there. So when we generate this, let me check. So this function actually generates like and fills with random values all this stuff. Yes, we create 8 such transactions in a slice, and then we capture the immutability snapshot of it or checksum. Yeah, so for attachments, we have yeah, we have like one like string to some struct, which has also string inside, and the other is like a string to some byte slice. So that's it. What else? For context, you can see we kind of create 1024 elements filled with kind of strings, and these strings can be 4 kilobytes, up to 4 kilobytes, but then as I would say they are kind of 2 kilobytes on average with size. Okay, so that's it. And then we started to run some benchmarks. So as you can see, if we go back here, this was our like original results. What is interesting about this result? So for example, when we capture string, so for 16 kilobytes test case, where we capture string snapshot and also origin, we kind of spend 2 milliseconds on it. If we just capture origin, it's almost the same. As you can see, if we have any mutations, we spend more time. That's obvious because we kind of need to generate diffs and allocate panic and so on. Okay, so when we don't capture string snapshot, we kind of travel from 2 milliseconds to almost 9 microseconds, which is great. As you can see, yeah, if we don't capture string snapshots of a value, it's a massive time saving for us. Okay, what else we can see from it? Yeah, so we're kind of on 7.5 microseconds, or 7 microseconds and a half if we have no mutations. Once again, if we have some mutations, we kind of spend some time allocating stuff. And we can see a little bit different situation um, for transactions, because in transactions, as you can see, there is some kind of a, we will see the results later on, but as you can see right now, there is almost no difference if you kind of capture um, yeah, if you capture string snapshot and everything and origin or not, it's kind of almost the same results. So we'll need to take a look at what is happening there. Here is allocations. As you can see, we do a bunch of allocations, and even like for byte slice, we do even more than for transactions. So we will need to take a look at once again on that one. So first thing that I've done was I kind of started to look at what is happening, and I found that a lot of time in the profile, a lot of time and allocations that we create in reflect deep equals method that we use um, to compare our checksums. Apparently, a current implementation of reflect deep equals, it allocates, like when it compares, and yeah, when we basically walk through the reflect map representation, it allocates and makes a copy of every value and every key and every value in a map. And that's why we kind of make a lot of allocations because of that. So in order to fix it, like I was kind of forced to implement um, yeah, I was kind of forced to implement my own checksum comparison function. So you can see here we had like a deep equal comparisons. Now we have our own code to our own function where we know the exact type of these maps, and we walk them on our own and produce the result if these two snapshot or kind of checksum maps are equivalent or not. And we have a short case, like shortcut when these checksums have different size and so on. So this only, like this thing already helped a lot. I can see that we kind of doing a little bit a bunch of other things. I don't remember why. Um, Maybe when it's some kind of a, it is some kind of a optimization, but it was very small in results, so I don't even remember that it produces any kind of measurable difference. Yeah. So the most of the gain that you can see here goes exactly from equals methods. And as you can see, what we have here, the actual absolute time difference is not as big, but you can see that, for example, in cases where we kind of capture string snapshots, it's not as noticeable. But yeah, that's because like most of the time we spend actually yeah, because the actual checksum capturing and comparison is minuscule in comparison to actual string snapshot gathering. So it's only noticeable and noticeable a lot when we start to just do actual work, actually capturing checksums and comparing them. So in that case, we see like some improvements, like 7%, 6%, and so on. Yeah, 7%. For transaction case, we can see like 9.5%. So yeah, something like that. In terms of allocations, we can see that we kind of do almost 2 times less allocations in some cases. So yeah, if you are interested in more details, you can check out this code. You can run these benchmarks on your machine and so on. Yeah, but that's the results that we get. So for example, in that case, when we have we have a lot less allocations. That's for sure. And you know why the difference is so staggering between just like one byte slice and a bunch of like transactions and nested objects, and the difference is so significant just because of size of actual maps and actual checksums. So here we kind of have only few elements inside the actual checksum map. So we do allocations, but we do them like instead of 19 allocations, we do 11 allocations, and that's it. But when we have a huge transaction for and this like 1,000, so we have 8 transactions, and every transaction has 1,000 strings inside and plus some other objects. It means that we actually have a massive checksum map that has like address of every string, address of every transaction, and other snapshots and so on. That's why these maps are really big, and when we have used like reflection to compare these values, we allocated a lot of keys and values copies to walk through this checksum map. So that was the difference, and you can see here we were doing we were doing like almost to 28,000 allocations per operation basically, and here we have 10 times less actually, and that's where we have mutations. Where we don't have mutations, we do even less than that. So yeah, maybe it's not reflecting as much in the actual runtime, but or absolute running time of the benchmark and every operation. But in terms of allocations, that's a lot, and that's a lot of like overhead and influence on the garbage collector. So yeah, I think if we would have some other more other code that would work apart from this checksums thing, it would slow down because of amount of garbage that we create and so on. So that's the change. It was super small. So basically, like avoid walking through maps using reflection, because that's very slow and allocates a lot of objects. But this is also a case for other maps. So we basically, when we want to capture snapshot of any map value, we will do this additional copies and allocations, and there is no way for us to optimize that because we don't know the actual types of these maps and so on. So I have few things in my mind how we can kind of deal with common cases of maps, but we will see what we can do later on. For now, in our benchmark, we have maps only in this transaction, like a map, how it was like map execution context had like some small map inside. So we kind of have them present, but are not like dominating the actual case. Um, yeah, there is already proposal in Go to add additional methods to the actual reflect that will help us uh, potentially avoid unnecessary allocations there. But this proposal is already in the status likely to accept, but it's still not accepted. And I think even if it's going to be case, it will be targeted to Go 1.18. So we'll see. Um, okay. So that's it with the first set of changes. The other set of changes was to reuse snapshot objects between actual runs. So what we do here, as you can see, so we started to use bytes buffers instead of strings for file and string snapshot, and we started to capture these snapshots into the byte buffers. So then we can when we reset snapshot, we can reset internal buffers, and that's it. Yeah, this is very useful and easy to do. Then we changed the code to work properly with byte buffer instead of strings. And then where it is, I think I moved this equals method down to the end of the file. And then we have a global pool of snapshots. And yeah, inside this global pool of snapshots, we basically, when someone calls ensure immutability, we take two snapshots from this pool. We initiate them with proper values. We capture checksums from there. We take one snapshot, we capture checksum into that snapshot. Then when someone calls the comparison function in their differ or by using any other way, we allocate the other. We basically take the other snapshot from the pool, and we return them to the pool, both of them. And then I think it's pretty self-explanatory what is happening here. The cool thing is that if our users using that ensure immutability function, they basically don't have access to the actual snapshot values, so they can't reference them or have any other reference to that object. So we know that this is the only function where these snapshots are visible. So we can manage them on our own, and no one can interfere or have another reference to our snapshots, and we can easily recycle them without any problems at all. So that's cool. But we also created additional methods on the actual. So as you can see, snapshot reset, value snapshot reset method is public. So people, if they want to use other methods, which is just, capture snapshot and then check this snapshot versus the other snapshot, they can still do it. And if they want to implement their own recycling and management of this snapshot object, they can do it, because we provide them visibility to clear these objects, and we provide them with ability capture them on their own and compare these snapshots on their own. So that's the case. Okay, this simple change, like relatively simple change, gave us one more staggering improvement in amount of allocations, as you can see. So previously we were doing kind of 1000 allocations in transactions thing. Now we are doing 400 allocations or so. Similar thing goes in yeah, similar results we can see with byte slice. So yeah, that's our result. Okay, let's go further. So here, this change, I've done this change, but the actual difference was so small that I decided to not like highlight the actual results, but I still think it's neat and maybe it will enable us to do some other potential improvements later on. I don't know what is happening with GitHub. Can we open that one? No. Yeah, that's very weird. Sorry about that. We are back. GitHub had like a few seconds of some problems, so let's get back to that change. As you can see, the actual change is super small. I decided to get rid of checksum key structure and just use regular uint pointers, because checksum key, as you can remember, maybe it was a actual pointer. I mean, like uint pointer plus a reflect value kind. So now when we are using just uint pointers, we are able to use more efficient map access methods. So we're basically using like fast 64 method from Go runtime to access, to basically update this map and compare the results. That's the main change. Yeah. So we basically pack everything into one, like 64 bits, and I can actually show you the results because I just removed them from the. Yeah, so as you can see, if I can view actual file, as you can see, results were almost the same as they were before, with the, yeah, almost the same as they were before, except maybe yeah, we are doing less allocations. Oh, okay, I remember. The allocations thing, it's a separate thing. So there is like one line change that gave us these allocation improvements, but it doesn't reflect in any runtime speed or anything like that. So allocation improvement goes from not from changes in how we pack values, because this is kind of a non-pointer, just plain old structure. The change in allocations comes from that method. Yeah, that change here. So here, where we try to figure out the pointer to the actual value. Previously, we checked that, okay, if we can get an interface to the value, then we will take this interface and we will use unsafe to get a pointer from this interface. And then we were checking, okay, if we can get an address directly from the reflect value, then we get an address. But apparently, this method, we actually rarely come to that point in the code. We usually resolve all addresses here, like way before that. But for some small amount of values, we go here. And apparently, this can interface, like the getting the interface from reflect value and then capturing the pointer from it actually creates a small allocation on a heap. So just by like, and for most cases, this approach will work as well for, yeah, will work as well. So we just change the order how we do things. So this thing produces no allocation, and only if we didn't manage to get address directly, then we go through interface hack. Yeah, and in that case, we get less allocations, much less allocations. And that, yeah, this is cool. But it produces no actual speed up or anything like that, but we produce less heap garbage, basically. So that's cool. Okay. And the last change that I've done, so I looked at the CPU profile of this case, for example, where we just work on. Okay, one thing that you can maybe notice that these values will be much better than the values from the previous result. The reason is because we started to use Go 17 or Go 1.17, and we get from 15 to 30% improvements in our benchmarks just by using the new version of Go. But I don't highlight it anywhere just because we get this improvement not by doing our work or changes, just by getting like better compiler that can do much better work with inlines and better work within the calling convention changes that were introduced in 1.17. So yeah, we got a lot of improvement there. So as you can see, we kind of right now in the range of like 3.5 microseconds for 16 kilobyte bytes buffer. Yeah. So I started to profile I started to profile this particular case, and I noticed that we kind of spent a lot of time, most of the time, in actual hashing. So when you look at CPU profile, the CPU profile is dominated by hashing algorithm, and we were using map hash, which is like a standard default hashing function that is used for maps in Go. And I decided to change the function for the fastest that I know available for Go, which is XX hash. And just by doing one small change, we were able to get really good results. As you can see, we have 30% improvement in that particular case. It also improved other things because we are hashing strings and we cache a lot. So like 11% there. We also do a little bit less allocations, and that's because of I don't remember exactly. I looked into it, but I don't remember exactly. I think that's because of so previously we were calling like yeah, I can show it to you in the actual change. So that's the actual allocations part is related to the way how XXHash API is structured. So as you can see, we just I just added one additional thing. Yeah. So previously, as you can see, we were kind of allocating hasher, or yeah, allocating that object that we used for hashing. Now we don't do it. And that's the difference in actual allocations. Why don't we do it? Because, and previously I had like a plan to, start pooling these hashes, but I didn't even started doing that. That's because XXHash has a direct API that gives us ability to pass byte slice and get 64-bit hash. So we don't need to have a separate object of XXHash to produce these things. And that's great. Like, we don't need to do all these resets, writes, sums, and so on. We kind of have this part automated already. And I think we will be able to remove these to-do item as well, since now we don't allocate them at all. So yeah, that's the difference, just one small thing. And we have more, much better results. So now for our 16 kilobytes byte slice, we spend like kind of 275 microseconds. For our 8 huge transactions, we spent 5.5 milliseconds. So that's the changes that we have so far. Please take a look if you want to run these benchmarks on your machine. Get to our Telegram channel with comments, or just post your comments on YouTube if you want. Yeah, as you can notice, I also started to merge the most recent changes to the main branch. So now we have like the most recent changes there, so you can kind of point them, and people can take a look at what is the state of the project right now. But I still have like a separate PR for every day, so you can kind of look through all of them and check what's changed from every session and so on. So that's it. Thank you very much. And yeah, stay tuned for the next changes.